Okay, so today we are going to move into valence bond theory, hybridization, and molecular orbital theory. Okay, so we've already talked about electron configuration, where those electrons are located. We realize we're only talking about the valence electrons when, or not the valence, all the electrons, but only the valence electrons are the ones responsible for bonding. So when we talked about, charged ions, meaning which electrons from that configuration were given away versus gained, right? We were talking about those outermost electrons. Those are our valence electrons. All the rest are core electrons. So from here on out, when we talk about electrons, we're really only talking about the valence electrons, okay? So valence bond theory, there's a couple of main concepts that you need to know and understand. So the first one is that we know we get these S, P, D, and F sublevels in their fixed main energy levels. And there will be, which we're going to do in a few minutes, a hybrid combination of these. What do I mean by that? Well, they're literally going to hybridize into one bond. So if you remember, S was a sphere, P was that figure 8, D was the 4-leaf clover, 2 figure 8s put together, right? So if we were to look at, say, hydrogen has how many electrons total? Look on your periodic table. How many electrons does it have? 1, okay? So that electron is in what fixed main energy and sublevel? If we were to write the electron configuration for hydrogen, what would we say it is? What would it be? Grab your periodic table, get it out, look at it. What would its hybridization, or not its hybridization, its electron configuration be? 1s1. Anybody agree? Yeah, if we use our little trick, first box, first row, super simple, 1s1. So that means the one electron that hydrogen has is going to be in this spherical orbital. Okay, so here's the sphere, here's the other sphere. When these bond together, they're actually going to overlap. So we get kind of this overlapping shape, where if you can imagine, it goes from a circle to more of a this, I'm terrible at drawing it, this sort of shape. And they will wind up overlapping in this area to form kind of an elliptical, very bad drawing, but kind of sort of an elliptical, okay? That's a hybridized bond. So the second important thing, a chemical bond results when 2 of these atomic orbitals interact and there's 2 electrons in the new molecular orbital. There's got to be 2 electrons for each bond to occur. That should just be common sense, right? Electrons must be spin paired. What do you think I mean by that? How do I draw how do I represent the electrons when I was doing electron configuration?
Up and down.
Up and down. I had a half arrow, which represented 1, right? And 1 was up and 1 was down because they're spinning oppositely, okay? The shape of the whole compound is determined by the geometry of the interacting orbitals. And then valence bond theory, again, atomic or hybrid orbitals interact, or what we call overlap. Okay, the overlapping is the hybrid. Okay. In order to overlap, one of these two things, one or both, must apply. You need to know those. Okay, they have to be aligned along the axis and be parallel or perpendicular to each other. Okay, and again, that's just kind of a common sense thing. They got to be close by in order to interact. So if they're perpendicular or parallel, they're in close enough contact that they can bond. Okay, why do we have to hybridize? Why? You can see the word inconsistencies right here. There's inconsistencies present. So I just want to remind you when you see this, in case it's not very clear, if you remember when we went over the shapes of the orbitals, the S, P, D, and the F, if you remember, I wrote P on the X, Y, and Z axis. And remember when I did the electron configuration, P can hold 6, so I had 3 lines because it was paired. Okay, that's what this indication means. This is the P orbital on the x-axis, the y-axis, and the z-axis. So don't look at that and say, that looks weird, I have no idea what it means. That's all it's doing. It's just kind of spreading it out where we did not, okay? The inconsistencies are what happen when we have half-filled or unfilled orbitals. That happened with oxygen. If you remember, oxygen for its 2p only had 4. So we have these two only half filled, right? So you don't get to predict the number of bonds or orientation of the bonds because of these inconsistencies. Because of that, we do hybridization. It kind of corrects it. So let me see, hold on, let me just see if there's going to be a picture coming up. Okay, I just want to look at this really quickly. Forget the sigma and pi, we'll get back to that in just a second. I just want a 3D picture. Let's just pretend these, okay, we'll say there's a carbon here and a carbon here, and they're separating these out, okay? And actually, let me do this. Let me color code this. Okay, that's my those are my double bonds, and they're going to be between 2 carbons. I'm totally just using this as a generic example. Now, the bottom one here, that is representing the green bond. And the other one up here is representing the second bond. Okay. Now, if you can imagine, and it's hard to really kind of see, the red line I drew, that is my pi bond. It's done with the p orbitals, okay? So if I have 2 carbons, this first one down here is going to be this overlapping of the 2 electrons that are in the s orbital. Then, because it's figure 8, that p pathway, it overlaps here and here around the carbons. Okay, so these are hybridizing. You can kind of see where that figure 8 is right there. right? And you can kind of see if this were a pi bond or p orbital, how they would overlap this way with the first bond. In my example, it's a sphere, okay, because it's carbon. So you can kind of see how this overlapping is going, okay? It can become a little confusing, but I will make it as easy for you to understand as I can. Okay, so if you have unhybridized orbitals, we're going to use CH4 as the most common one, the easiest one to kind of really look at. Here we have carbon, hydrogen, 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 hydrogen. Those are my 4 hydrogens. We get this 109.5 angle between them because of hybridization, attraction, and repulsion. Okay, those are the 3 things. So normally, a lot of students, when they first start writing Lewis structures, and you guys might do this too, just write it like that, right? But we know that it's really going to be like that. So where is all this coming from? Well, hydrogen has 1 s, and carbon has 2 valence electrons. These are valence electrons for carbon, okay? Those are part of the core, kind of. So if you look on your periodic table and you see carbons in what group? What is it? 14? Okay, so how many valence electrons does group 14 have? 4. So there's 1, 2, 3, 4. How many electrons does carbon want? How many does any element want? 8, right? So that means there's the opportunity for carbon to bond with 4 other hydrogens, okay? Because then it'll have the 8. So we have different types of hybridization that can occur. SP, SP2, SP3, SP3D, SP3D, SP3D2, okay? Now, if you remember, I showed you guys this in class last time, right? SP, this whole grouping is SP2, this whole grouping is SP3, SP3D, SP3D2. Look at the relationship here. There are 1, 2 things attached, and it's SP. 1, 2, 3, or 1, 2, and a lone pair, 3 things, SP2. 1, 2, 3, 4. 1, 2, 3, and a lone pair. 1, 2, and 2 lone pairs, SP3. They all had 4 groupings. It's 1 less, SP3. 2 groupings, SP. 3 groupings, SP2. Do you guys see the pattern? Okay. 1, 2, 3, 4, 5, 6. 3 plus 2 is 5. It's 1 less than the number of surroundings. Okay. Here, 1, 2, 3, 4, 5, and a lone pair makes 6. Still SP3D2. Okay. It's the easiest way to remember these. So why would it be that they say the same type of atom can have different types of hybridization? For example, carbon can be sp, sp2, and sp3. Why would there be differences? This carbon is sp3. That carbon is sp. Why is it different? Why can one element have a different hybridization?
Does it depend on what element it's bonded to?
Yeah, exactly. It depends on what's going on. This carbon right here, it's bonded to 2 oxygens, CO2. This carbon right here is just like the methyl group we just saw, CH4. Depending on what it's bonded to will affect what its hybridization is. And that's true of any element. Okay, so again, just kind of the takeaway here, look at what's going on. You have an s orbital and 4 p orbitals. I'm sorry, 3 p orbitals. One on the x-axis, one on the y, one on the z. Okay, now, when these all hybridize, we're going to get these kind of shapes coming together. Do you see how they're just completely distorted? They relatively, except for S, they relatively maintain that figure 8, but just with one side significantly smaller than the other. They're all going to come together to hybridize like this. Okay. How many of you guys in here have to take organic chemistry? Okay, well, if you're a biology major, I know you do. I highly recommend now go ahead and getting a molecular model kit. They're super cheap. You can get them on Amazon for like less than 20 bucks. Because you're gonna need it in organic 1 and 2 anyway. It's just gonna help you. But even now, if you were to build this with your molecular model kit, you'd see how this shape comes about and not the 90-degree angle. And it all has to do with what's attached and how it hybridizes. Okay. All right, so I want to show you guys a short video. So hold on. Those are the crystons. Okay, so now why isn't the sound on? Are they on? Or did they just take them? Oh, well, okay, so hopefully you guys can hear this because it's coming out of this speaker, not the ones on the wall, and I have no idea why. It's this one. That's fine.
More explicit.
Nope. Okay, so hopefully you guys can just hear this. Oh, that's not right. What do you think? It says it's going to use all 3 p orbitals, but there's only 2 orbitals that have electrons in it. So first, how is it going to use all 3? Say it again. I cannot hear you at all.
Take one from the S and put it to B.
Not quite. We're not taking one from the S. Where are those 1, 2, 3, 4 missing electrons going to come from to satisfy the octet? We just said it a few minutes ago. What has to happen in order for hybridization to happen? Can an element all by itself hybridize? What has to happen with that element? It's got to bond. So these electrons that are missing to not have an octet are going to come from something that's bonded to. Okay? So where are we going to put these other things? Where are we going to put them, up here or down here or somewhere in the middle? What do you think? Say it again. I thought you said something. You didn't say anything. You think the top? Okay, anybody agree? All right, let's find out, shall we? They said at the top. Okay, so why not just all the way up top? It's up towards the upper ones. That is correct, but it's not here. Why is it here as opposed to here?
It's only 75%.
Because it's only 75%. Remember, it's a hybridization. 2 things are coming together. So it can't be an either or. But it's mostly P character, so it's going to be higher up, further away. Okay? Can't be all the way 100% because there is S character there. So it's got to be mostly towards the top. Okay, he said 2 things so far. He said Heisenberg's principle and Hund's rule, right? Okay, Heisenberg principle talked about it in terms of probability of where an electron would fall, like where we would be able to find it. Heisenberg's principle states we cannot know the exact location of an electron at any given point. So think about it this way. If I had two bottles, like Coke bottles or water bottles or whatever, and I stuck them together open end to open end, and there was a fly in there, right? Those two Coke bottles or water bottles would basically make kind of a figure eight, right? Okay. Somewhere in that figure eight, that fly is going to be flying around. We don't know exactly where or when or how or why, but we know there's an enormous probability, almost 100%, we'll find it in that bottle. Okay, that's the idea behind that. Hund's rule, along with off-ball, which should be coming up here in a minute, states we must fill each orbital first singly, then go back and double up. And then also the spins will be opposite of the electrons within a pair. Okay, that's the long and short of it. I hate these. Remember, we're still doing this all in terms of carbon. You might want to write that down. You need to know this also. Okay, what do you think? Think sigma is stronger? Okay, then that, okay. Anybody agree? Anybody disagree and think it's the pi bond? Okay, let's find out. They said single. Okay, does that make sense? Okay, when they're all together, again, hold 3 pencils in your hand and try to break it, and it's exceptionally harder to do than a single pencil, right? But if I just take my 1 sigma pencil and my 1 pi pencil, the pi is going to be much easier to break because it's got much less energy and because of the way it's oriented. Go ahead and draw it and answer the question. How many sigma and how many pi bonds are there? No, your way. I always feel like I'm like blocking the board from you seeing it. Okay. Okay, everybody got it written down? You think you know how many sigma and pi bonds are there? All right. Did you get it? Okay. What if this had been a triple bond? Right, that would be 2 pi's plus this one over here, so a total of 3. Okay, it's a quick and easy way to look at a compound and just know how many sigma and pi bonds are present. Okay. Okay, so no. Okay, so this 3-dimensionally is what this would look like. This is your Lewis structure. This is ethine. Okay, so here's the carbon, here's the carbon. This purple in here is your sigma bond. okay? And it's like kind of think of it like the middle one, right? Where the s orbitals are just overlapping. And then you get these pi bonds. I need a different color. Seriously? Why isn't... Okay, it's not letting me click. So this, I know it's hard to see, I'm sorry, belongs with that one. Right, so they're overlapping here and here. Now I can do it. And these ones down here are on a different axis, and it's really hard to see. They're kind of coming out. So can imagine it going back in, like into the computer screen, or into the screen and out towards you. All right. And so then these are overlapping. Like I said, three-dimensionally looking at these pictures is really confusing. But just have that general concept in your head that when the overlapping is occurring, it's above and below the element. And then the third one is overlapping dead set in the middle. Okay. I'm never going to make you draw any of these ever. Don't worry. But you do need to know, like, for example, if you have this 1, 2, 3, 4, 5 things, it's sp3d. Okay, so if I give you a structure, you got to be able to tell me what kind of hybridization it contains. If I give you a structure and I ask about a particular element in the structure, like the ones you guys just wrote down, if I asked about the carbon on the right of the double bond, what its hybridization was, you need to know that. Okay, now the other thing you have to remember is that when you're looking at the big structures, lone pairs of electrons are not written, right? So you'd have to make sure you would know if that particular element has a lone pair of electrons or not. And you're going to see that most frequently with nitrogen, oxygen, fluorines, chlorines, etc. Okay. Do we have time? Okay, I'm just going to introduce. Okay. Where does it start? I'm so hungry. Valence bond. I'll start here. Okay, I'm just going to introduce molecular orbital theory, and then we'll actually do the examples of it Wednesday. Okay, so remember when we talked about Lewis structure and Vesper and how it can't handle odd number electrons? There's lots of problems with that. So now when we're really wanting to see what's happening when things come together and bond, we're going to use molecular orbital theory. So in molecular orbital theory, you need to think about electrons as a wave. Okay? Remember, he said that, and you're going to hear it again and again and again. You got to think about them in terms of a wave. And we'll get to why in just a few minutes. But just keep that on the back burner. So Schrodinger's wave equation and molecular orbitals. Okay? Schrodinger's wave. You guys have heard of Schrodinger's cat, right? Anybody not know what Schrodinger's cat is? The cat is either dead or alive until you open the box, right? Okay, people are making jokes about, Schrodinger's COVID. You either do have it or do not have it until you get tested. Okay, so the idea is, it is and it is both not doing something until it actually happens. Okay, so look at what it says here. we have estimation, which is as best we can get, right? And then once we get that estimation, it's evaluated and adjusted until we get the lowest minimal energy used. So in the same way it's easier to go down a mountain than climb a mountain, it is much easier for electrons to drop down first to lower energy than it is for them to go higher with higher energy first. They're not going to do it unless they have to, or unless energy is put in and they're energized. Okay. So with this treatment, the electrons belong to the whole molecule. So the orbitals belong to the whole molecule. We call this delocalization. And what that means is no one electron is independently on its own to an element. Everything is all together. Kind of like when we were drawing the Lewis structures and we first counted up all the possible valence electrons that were present, right? It becomes, you throw everything into one pot and everybody gets a part of it. Okay? Okay, so we're going to have bonding, what we call bonding and anti-bonding orbitals. Okay, the bonding are the lower energy, and they're either going to be sigma or pi. And the anti-bonding are what we call sigma star and pi star. Anytime you see these stars here, you know two things. One, that it's anti-bonding. And two, that it's higher energy. Okay, those are the two things you know when you see that star. When you have bonding, you have most of the electron density between the nuclei. So what do I mean by that? Remember, I've already written once that when hydrogen bonds, the bond is going to look more like this weird eclipsed thing, right? Okay, why is that? Well, if we look at hydrogen in terms of its nucleus, which is positive, its electron, which is negative, and here's the other one. That's the nucleus, which is positive because of the protons, and there is its one electron. Now, what's happening is we got a couple of forces going on here. So the proton here is being attracted to its electron. It's also being attracted to the other hydrogen's electron. So that's one force. And then the force to the other one. Okay. But that proton is also being repelled by this proton. So it kind of wants to pull away. Okay. Now, the other hydrogen is doing the exact same thing. It's saying, okay, yeah, I don't really want to go towards that proton either. So there's a force of repulsion. But then it says, but I really, really like the electrons. So it's going to be attracted this way and attracted that way. So we have 1, 2, 3, 4 forces of attraction. They outweigh the 2 repulsions. Okay? So the hydrogen, the electrons are going to be found between the nucleus. Why does it keep doing that? There. The nucleus of the 2 bonded hydrogens in your bonding molecular order, the lower energy. In your anti-bonding, it's going to be the opposite, where the forces of repulsion are greater than the forces of attraction. Okay, so here, this is where we'll find the electrons for this one. Your anti-bonding is going to look like this. Where the electrons are going to be outside. Okay, not in between the nucleus, on the opposite side of the nucleus. And their shapes, that's a really bad picture. Kind of like look like D's. Well, a backwards D and a regular D. Okay, and it's not going to be between them. That's the takeaway. We get anti-bonding with destructive interference. What do I mean by that? Remember I said to remember or think of electrons as a wave? Well, if I have two waves and they are not in sync, right? So this is up positive above zero. This is negative below. What we're going to get is this anti-bonding due to deconstructive interference. So the electrons are not between the nucleus. With constructive, that's when they're in sync. Their waves are in sync. So I'd have one that's doing this, another one is doing this, and they're going to come together and just form this kind of ovalish shape where you do get the electrons in the nucleus. Okay. All right. I'm stopping there. We're going to do examples on Wednesday. And that's all we're doing on Wednesday is the molecular orbital, I don't want to call them charts, but go through your book and look at those that are there. Okay, I want to say page it starts on page 273 or 274, something like that.